Hello everyone. Can just anyone drop a message if we are audible? Yeah, are we audible?
I can't hear you.
Yeah, we are on. Are we audible? Okay, so let's start with it. Namaskar, good evening. I extend a very warm welcome to everyone. I hope all of you and your families are safe and healthy during this COVID-19 pandemic. I am Sachin Motwani and under Secretary at IEEE Signal Processing Society Delhi chapter and your host for the day. We also have with us Dr. Anubha Gupta, Professor and Dean of Academic Affairs at IIIT Delhi, the Chair of SPSDC. Today, we are having an exciting webinar on signal processing for flood forecasting in India, hosted by IEEE Signal Processing Society Delhi chapter, to be delivered by Professor Ami Wiesel from the Hebrew University of Jerusalem, Israel. Before I introduce our esteemed speaker of the day, I would like to inform that IEEE Signal Processing Society's core objective is to educate the signal processing community and provide a platform for enthusiasts to interact and exchange ideas. IEEE SPSDC's aim is to forward this objective to even larger audience through its events and workshops. Today's speaker, Professor Ami, received the BSc and MSc degree in electrical engineering from Tel Aviv University, Tel Aviv, Israel in 2000 and 2002 respectively, and the PhD degree in electrical engineering from Technion Israel Institute of Technology, Haifa, Israel in 2007. During 2007 and 2009, he was a postdoctoral fellow in the Department of Electrical Engineering and Computer Science, University of Michigan, Ann Arbor, Michigan, USA. He is currently an associate professor in the Rachel and Selim Benin School of Computer Science and Engineering, Hebrew University, Jerusalem, Israel. Since 2018, he is also a visiting researcher in Google. We are extremely thankful to Professor Ami to accept an invite for delivering a talk. Hello, sir. IEEE SPSDC is honored to have you. Now, I would request you to start your screen and go ahead with the webinar.
Thank you very much. Can you hear me?
Yeah.
Great. So thank you very much for having me. I'm sorry it's only virtual, but it's very exciting. I hope one day to actually see your faces. I'll tell you about our work on signal processing for flood forecasting in India. It was mostly done in my sabbatical, which finished about half a year ago in Google, where I worked in Google Tel Aviv in the flood forecasting team. So this work is, of course, joint with Hebrew University and Google Israel, and also people from Google all over the world, including Google India. In particular, I want to say thanks to the floods team who hosted me during my sabbatical. Galil, Idan, and Sela Nevo were my hosts, two amazing engineers in Google. Sela is the one who envisioned the flood forecasting initiative, and everything you'll see is led by him, and it's quite amazing. I will say from the beginning, a disclaimer, I'm not an expert in the flood forecasting part. I'll talk about it a bit, but mostly about the theoretical part. If you have more questions, then I can direct you to the flood team engineers. Specifically, I will talk about two works in signal processing, about robust signal processing by my students Yoav Vold and Nofar Noy, two amazing students who did most of the work. And the first part would be on common signal processing. I will explain soon what that means, by Yotam Gigi, another student of mine. All of them are also, except Nofar, working at Google. On the left, what you see is an Israeli flood. Now you guys are in India. I guess that's not what you envision when you think of a flood. So that's not a flood like in a big river, but that's actually a flood in the desert. This is a special place. What you see there are the group of the flood team in Israel, and this is a place in the desert in Israel where there was a flash flood a few years ago, and 10 people died. Now, a flash flood is when there's suddenly a lot of rain and the water breaks. This is not the kind of floods that you have in India, and not the kind of floods that I'm going to talk today about, but it's just to show you the group members. So this is all the tanks. And let's see what we're going to talk today about. So the agenda today will have 3 parts. I'm going to briefly talk about the flood forecasting initiative in Google. It's really going to be brief. I already left half a year ago, so they've done a lot since then. So this is a bit outdated, but just so you'll get the main idea. And then we'll talk about the 2 signal processing parts, about common multitask regression and robust multitask regression, which is the part I think that most of you are interested in professionally. Okay, so let's start with the flood forecasting in general. So you guys probably know it better than I do, but before joining Google, I didn't know the impact of floods all over the world, and especially in India. You've got some numbers here. So apparently from all the weather-related disasters on the world, floods is the worst one. You see here a number of people affected by disasters. So you see floods is much larger than the rest, especially in India. And I think that was the reason that Google decided that they sort of, what project can we do to save a human life? And the flood seems to be a place where there is a lot to do, even using simple tricks, which are easy for Google, but difficult outside, to change the world. So the Google Flood Forecasting Initiative, the goal is to develop a system of scalable, something that will work in large scales, global, high accuracy, will be very accurate without a lot of false alarms. High resolution will be able to tell you exactly in which villages will be flooded, which will not. Flood forecasts and warming globally. So basically, we want to be able to forecast floods as early as possible, giving a lot of accuracy, warning enough time in advance, and with good resolution, so people will know exactly which places they should evacuate or not. As I said before, there are different kinds of floods. There's flash floods, riverine floods. Specifically, right now, we are focusing on riverine floods, which happen in big rivers like the Ganges, and completely different from the one I showed at the beginning in Israel, which is flash flood, and we are not working on that yet. Okay, it's a bit slow. Yeah. Okay, so let me, in a few slides, give you flood forecasting in a nutshell. I'm not an hydrology expert, and the truth is that no one in the team was originally. Now some of them know much more about it, but I'll just give you flood forecasting like 101, the simplest ideas. So basically, the system is built on 3 ingredients. The first one is physical measurements. This is done mostly by the Indian government, the Central Water Commission. You see their icon there. And what they do is they have these sensors, these measurements, and they measure the height of the river, the volume of water that passes, the discharge that's how we'll call it, the discharge level in the river. These are all related concepts. And they give you these measurements, and our goal is to say, suppose the river is this height, what's going to happen in 6 hours, and what's going to happen outside the river. Is it going to get flooded? Are villages close to the river going to get flooded? So this is the physical measurements, and now how do we do the forecast? We do it using two parts. The first part is an hydrological model. What is an hydrological model? That's a model that takes into account the precipitation, the rain, the snow, the kind of soil, how the water propagates over the ground, and takes into account all these factors, historical factors, and tries to estimate what's going to be the height of the river, what's going to be the discharge in a particular moment. So, for example, if you know that the last 2 days you had lots of rain, then you can predict that the river is going to be, I don't know, 1 meter, 56 inches high, something like that. That's the hydrological model, and basically it takes all the inputs and tells us the height of the river or the discharge level in different points in the river. This still doesn't tell you anything about what happens outside the river. And that's the inundation model, the third part. The inundation model basically takes the water in the river and runs the simulations and tells you how the water is going to run throughout the geography next to the river, which villages are going to be flooded, how is the water going to run on the map surrounding the river. That's the inundation model. So let me spend 2 slides on each of these parts. Okay, so hydrological models, the classical approaches is, as I said, they have lots of components, all that have to do with physical ingredients. They take the rain, the snow, they see how much rain is going to come at some place, how much is going to go down the earth, down through the earth, and how much is going to propagate. And they do all these computations, and at the end, they give you a number, what's going to be at a specific point, what's going to be the height of the river. Usually, they have lots of components, lots of physics, lots of parameters. All these parameters you don't know, so what you do is you calibrate them using measurements. The measurements you get, for example, from the physical sensors I talked about before. And that's a classical hydrological model. At the beginning, we tried to do something like that, and we quickly understood that today it would be much easier to do this using machine learning. And indeed, a big part of our group, what they do is they do hydrological forecasting using deep learning, LSTM, deep neural networks. We have a few papers on that in ICLR 2020, I think in ICML. In the workshop, we had a paper on that showing that LSTM, if you develop them in a smart way and you share a lot of information from different places, then they really succeed to beat classical physical models. So this is the hydrological model. And the third part is the inundation model. The inundation model, it basically shows you how does the water propagate on the map. And this is where you see where Google comes in. Google has Google Maps. What we need here is something much more advanced than Google Maps. We need a DEM, that's a digital elevation map. It's a map that also tells you the heights. And you see exactly the river here on the right. And you see a mountain next to it, and maybe some island in the middle. And Google has this in a very high resolution and good accuracy. So we know the exact map, and this map can change over time. So we know that it's also very accurate and timely. We get it from satellites and stuff like that. And now, if the hydrological model tells us that somewhere in the boundary condition, the height of the river, now, if you learn physics, now you can start running a differential equation that you see on the right bottom here that tells you how the water propagates throughout the map. Okay, so all you need is boundary conditions, you need the map, which Google has, and you need a lot of computational resources because you need to solve this in very high accuracy. And Google has got lots of computers, and we do all these computations offline. So basically, what we get is a few measurements. We get a few measurements. Using them, we calibrate or we fit the hydrological model. The hydrological model forecasts the level of the river in a few points in the map here, and then we use the differential equation to see how which models we kind of solve an inverse problem, which situations correspond to these measurements. And then we know exactly which areas are likely to be flooded. Okay, here is a simulation. It's not running. Oh, sorry. So because this should have been a real-time simulation, but it doesn't work because we have a problem here in the presentation. I'm not actually playing the keynote. But you can see it actually if you Google, just Google flood forecasting in India, you can see this video, which shows you how the differential equation evolves in time over a real river. This was supposed to show you exactly the simulation. And once we have these simulations, now we know exactly, this is a real-time alert from 2 years ago in the Patna region. You see the Ganges River in the middle, and you see every place that we draw in red. We believe, our model says that there is a high risk of a flood. If it's like pink, then it's a medium risk of flood, and otherwise there is no risk. We had really good accuracy, 95% recall, 90% precision. A year and a half, in 2 monsoons ago, we did this. This was running on a first pilot only in the Patna region, a 30-kilometer by 30-kilometer region, where we gave out notification like that for anybody who looked at Google Maps or had Android. Then last year, I think we had like 10 times this amount of space, and we managed to do it in many more sites. And in the upcoming monsoon period, I hope we'll be able to do it even in a much larger scale. I should say at this stage that up till this year, we only did the inundation model. We didn't do any hydrological model. The estimates of the height of the river were done by the Indian government. So the only thing we did up till now was the government gave us the height of the river, the boundary conditions for the differential equation. We used our maps, the computational power of Google, and we simulated all the possible maps and how the water propagates on them. And then using that, we could output a map of probabilities where there will be a flood in high risk or medium risk or low risk. Next, this monsoon season, in a few weeks from now, we'll also be running for the first time our machine learning algorithms that will also add our forecasting abilities and not only the differential equations. Okay. So that was a short preview on flood forecasting at Google. Again, I've left the team almost a year ago, so I'm sure by now they have many more impressive things to show, and you can probably Google them and get more information. But now I'm going to talk about the 2 projects I did in the sabbatical with my students. So the first thing is the common multitask regression. So the main problem in the hydrological model, as I saw it, was it's basically a regression problem. We've got we know the river heights and the discharge in the past. We know how much precipitation was, how much rain was in the last week, how much snow, and we want to forecast what's going to happen in the future. It's a kind of regression problem. We've got very few samples, but we've got many, many tasks. What do I mean? What do I mean by many tasks? We've got many, many sites because we've got many, many rivers. What we're going to do here, the common multitask regression idea, is to share information between all those tasks. And although each one has very few samples, together they have many samples, and you can solve the problem efficiently. So that's the first part, by Yotam Gigi, my student. Okay, so again, the challenges. We've got, this is the world. This is in blue here. You see places where we've got the sensors that measure water height, where we could try to learn and get a data set and learn regression tasks. But the issue is that each one has very few samples because we don't have a lot of historical data. Okay, and usually what we want is to be able to go deep into the future, or alternately learn from one place to another place. For example, you see in the United States, you've got many sensors, whereas in India, you don't have many sensors. And we want to learn a model using the data in the United States and kind of transfer it to India. That was like the main challenge. Our idea was, we don't have a lot of data because most of the places we don't have sensors, or they don't go a lot back into the past. So we said what we do have is satellites. Let's try to estimate the water discharge levels given satellite imagery. Specifically, what you see here on the right, see there's a river and a highway passing over it. And we said, and below it, you see 11 images from a satellite called the Landsat 8. It's a multispectral satellite. So you've got 11 bands, RGB, red, green, blue. It's got also near infrared, shortwave, all kinds of images. Got 11 of them. And using them, we hope that maybe we can estimate exactly we look at the river. Let's estimate the water discharge. The problem here, of course, is that we've got lots of, these are big images, very noisy. As you see, it's hard to see anything in them. And we've got few data. So that's a hard problem. And we started looking at it, and we realized nothing worked. We always overfitted when we tried to do all kinds of fancy deep learning, or even linear regression didn't succeed because we didn't have enough data. It was clear that we need to somehow reduce the dimension of the data. And indeed, if you look at the images from Landsat on the left here, you see they look more or less, they're very, very similar to each other. You see the river in all of them, and you see clouds and lots of messy stuff. And so we started asking ourselves, how do we take all those images and see water from them? So we started Googling, asking people around, opened Wikipedia, and indeed there is something called a normalized difference water index, NDWI. Just take the near infrared image minus the shortwave infrared, divide this by their sum, and voila, you started off with 11 images. Now you get one image and you see the river very clearly. And now you have the dimension is much smaller. And now regression works very nicely. And indeed, this worked great. I think we had like something like 5,000 rivers that we tried on. I think in 80% of them, it worked really, really good. And that was a great solution. But in many of them, it didn't. And then you start thinking, why doesn't it work? And you look at this NDWI, and it says, take the near infrared minus the shortwave infrared. But why not take minus 0.9, the shortwave? Obviously, this is not exact. I mean, this is not physics. This is just somebody guessed. And if you actually look down below in Wikipedia, you see there's also modified NDW and all kinds of better indexes that gives you more specific values. In addition, we're actually not really interested in finding water. We're trying to find discharge or the river height. So we asked ourselves, why you use exactly this formula? Let's try to do a data-driven NDWI. And this is what I'm going to talk about next. So basically, we said, okay, we've got this XIT. This is a cube of spectral times spatial dimensions, okay? And this is all the data that comes from the satellite. On the left, we've got YIT, which is the discharge. This is what we want to estimate. We want to do something simple, so it's going to be linear. Let's just say that the discharge is take the image. It's not an image because it's you've got spectral dimension too. So take this cube, multiply it on the left by some W, multiply it by the right by some VI, and you have some linear transformation of the x's, okay? And this will give you the yi. It's kind of regression model. Only we decided that and this is the common part, that the W, now you see that we have YIT. I is the index of the site of the river. T is the number of samples. So we've got, let's say in our case, we've got like 1,000 river sites. I goes from 1 to 1,000. But each site has only, let's say, T, small t, goes from 1 to 100. These are the time samples. So we've got many sites, each with a few samples. Our idea was, okay, let the W be the same for all the sites. This is the common part. The VI, we're trying to learn W and VI. This would allow us to move from X to Y. But the W will be common across all the Ys. And the special dimension, VI, will be independent for each river, because some river is going from the north to the south, another river is going from the east to the west, okay? This will depend on the specific location. So this was our model, and you can see how we reduce the dimensions here, and you see the common part, which is W. Okay, we look at this equation, and now this automatically suggests the least squares approach. Let's just try to find the W's and the V. Now I just allow them to be matrices, not vectors, but it's the same idea. And now minimize them over all the indexes I, which corresponds to rivers, all the samples T, which correspond to samples. And now we want YIT to be as close as possible to W times X times V. That was our problem formulation. Well, when you start looking at it, you see that this is not a convex optimization. And this is where things start to get scary, because it's not clear whether we know how to solve such problems. For example, here I show you, maybe this is a objective has some scary landscape, and maybe it's impossible to solve it. What do I mean by impossible? Maybe every time you'll start at a different random initialization, you'll end up in a different solution, and you will not be able to efficiently find the global solution. So let's see a few special cases to show you that many people in signal processing worked on similar ideas. So the first special case is, suppose we had only one river. Suppose I equals 1. So now you erase all the I indexes. Okay, now it's just an optimization over W, one matrix W and one matrix V, okay, which both are common because you have only one side. Now you use the fact that the trace is cyclic, and you move the W to the other side, and you see that if you call V times W, you call it a matrix M, you see that M needs to be a low-rank matrix. Think of the case that V and W are both vectors. So this would be a rank 1 matrix, okay? And the question is, how do you solve a system of linear equations when you have another constraint that the matrix must be small rank? This work attracted a lot of attention over the last 10 years in signal processing, machine learning, and other areas. Specifically, we've got works by Recht and others that show that if you ignore the rank, then basically the number of samples you need should be B times P, their product. But because there is a low rank assumption, they show that the number of samples has to be only B plus P. So you need the sum instead of the product, and C is just a constant that depends on the rank. Let's just assume the rank is 1. And this is why this model is so successful, because you don't need B times P, you need only B plus P, and that's an order of magnitude, usually less samples, and that's why it's very exciting. And people show that this, although this optimization is non-convex, they can solve it, and they can guarantee that this condition is enough for perfect reconstruction. So this is one special case, the low rank model. Let me show you another special case in a completely different field, something called phase retrieval. This is the field, it's like the exact opposite. Now I'm looking at lots of rivers, but all the other parameters are 1. What happens, this is a bit harder to see, but what will happen here is that now VI will no longer be a matrix, it will be a scalar, and in fact it will only be able to be binary. So it's just plus minus 1, and you're just optimizing over W. What happens if you play with the equations is this is exactly phase retrieval, meaning the problem of finding W when you have measurements of yi equals the absolute value of W transpose xi. The absolute value comes because you also have this VI, which is plus minus 1. And this is very common in optics, where you only measure the amplitude. So we know that if you have like n unknowns, then you need n equations or n measurements to recover the unknowns. What Candes and Eldar showed in many works on phase retrieval, that if you only measure the absolute value, only measure the magnitude, and don't have the phase, that's why it's called phase retrieval, because you try to retrieve the phase, then now you need I must not be only bigger than B, but must be bigger than B times log I. That's the penalty you get for not knowing the magnitudes. So these are two special cases, and our work kind of generalizes both of them. I should say the truth, the idea is a bit different, but basically we follow their approaches, especially the works by Candes and Etropali, step by step, and just extend it to our setting. Both the algorithm and the proofs are very similar, just generalized. And indeed, the algorithm, again following Candes and Etropali, says the following, and this is not an iterative algorithm, it's a closed-form algorithm. We have 3 steps. Do cross-correlation between the labels y and the features x. Then average over all the sites. You multiply zi by zi transpose and take an average over the sites. And then take the leading subspace, just do a PCA, and take the leading, let's say we want rank 1, so just take the principal eigenvector. This algorithm can be used as an initialization for another gradient descent algorithm, or if you're satisfied with it, you can just use it as a standalone algorithm. That's what we usually do because we want a closed form solution. Okay, I'll skip this because I see we're running out of time. One thing that was different in our work and the low rank and phase retrieval works is that the previous work used measurements which they designed. For example, in phase retrieval, the xi, the data, is basically how you decide to measure the signal. It's going to be some Fourier or IID Gaussian variables. In our case, the data are images from a satellite. They're very, very far from IID. And indeed, when we ran the algorithm as it is, it completely failed. and didn't succeed because the algorithms rely very much on the IID assumptions. IID is independent and identically distributed. In our problem, we use it for regression. In regression, the features are correlated, and therefore we had to do some tricks before. Specifically, we did some pre-whitening. We first estimate the correlation. We do decorrelation. I won't go into the details, but we've got a lot of data here, and estimating the correlation is very hard because there are too many variables here. So we use something called the Kronecker model. It's very famous in signal processing. We use it all the time. If many of you probably do wireless, then we use it in transmit and receive antennas. We basically decouple the contribution of the two parts of the rows and the columns of the matrix and handle each of them separately. This significantly reduces the number of parameters. In a wireless, we usually do it on the transmit side and the receive. So in recommendation systems, you do it customers versus products. It's always rows versus columns. And in our case, the physical meaning here is spectral versus spatial. So we give a different correlation for the spectral side and for the spatial side. It's obviously an approximation, but that's, as you see, it works very nice in practice. Okay, so this is just the algorithm with pre-whitening. I'll skip this. And here is our main result. Again, based on the work by Candace and Trapali, which we generalized to our case. It includes all the previous special cases and generalizes them to our case where we have multiple sites with a common W matrix. And as expected, we get exactly what we want. The theorem basically says that I, the number of rivers, times the number of samples need to be larger and ignore all the constants and everything, needs to be basically larger than B, which is the dimension, the spectral dimension. Roughly, this means that instead of needing T larger than B, say you have B is 100, then you need one order larger than 100 samples to succeed. Now we exploit the fact that we have many rivers, and T has to be bigger only than B divided by I. In our case, think about it, T was usually around 60 to 100 samples, but we've got thousands of sites. So this significantly helped our cause. Okay, here is some data. CMR is our algorithm. We want to show you how it does better in terms of mean squared error with respect to full regression, or CMR1 is just doing everything site by site and ignoring the common part. And you see here that we are much better when the number of samples is small. We get to 31% error instead of 37% error. The difference is lower when you have lots of samples, and indeed the main idea here is to enjoy the common part when we have few samples. And here's a nice picture of the Ganges when we apply our algorithm. This is not, we take the Landsat 11 images, apply, just multiply them by the W that we learned that detects water. It doesn't detect water, it detects discharge, and you see exactly the Ganges. So this was very nice. The whole idea is actually when we finished this, we noticed that it's very similar to what people do today in convolutional neural networks. Because there too, you've got lots of, you've got lots of tasks. You want to classify, well, this is a dog, is it a cat, is it a human, or a table? And what most networks today look like, they have many layers which are shared across all the classifier, but then at the end, each class has its own local classifier. And indeed, the only difference from us and is that we're using Landsat, which is a spectral satellite, so we need many spectral bands. So we said, okay, let's do the same in image processing. Suppose you've got an image here of 6. It's a 28 by 28. This is from MNIST. So it's a 28 pixel times 28 pixel image. We reshape it into a 7 by 7 pixel with a depth of 16, which is the spectral dimension. And now we can apply our algorithm. What is our algorithm? You take the image, you reshape it, as I said, you multiply it by W, which is shared across all the tasks, and then for each class, you apply its own VI. And we learn everything in closed form by the algorithm I told you. Pre-whitening to make everything white, then in closed form we get the W's and the VI's. Let me show you how it works. This is MNIST, less impressive. Let's jump to SVHN, which is more impressive. Digits classification. This is, MNIST was very easy, but this is a bit harder. You see, we're not using the whole data set. We're trying to show, this is only useful, of course, when you have few samples. If you have all the samples, then just do deep neural network. Here we're trying to share a parameter, so it's useful when t is small. So you can look at, for example, when t equals 100, when we got 100 samples from each class, CMR gives you much, much better accuracy than full regression or just doing CMR1. When t equals 800, then there is less advantage to sharing parameters. Okay, that was about the second part. I think I have only 10 minutes left, or 9, so I'll run about quickly in the second part. The second part is, the first part was about, we had a few samples in the multitask regression. Now I'm going to talk about a different part, that we have, the samples we get are not only few, but they're also bad. What do I mean by bad? We've got outliers, we've got heavy tails, stuff like that. And you can think about what is a flood. A flood is the water goes like this, very, very slow, and suddenly it jumps, right? It's very, very heavy tail, very non-Gaussian. Linear regression, everything is a few samples, so we're going to do simple things like linear regression, and that's not going to work when you have a very heavy tail distributions. So this is the second part. So indeed, anyone who ever played with heavy tail data or contaminated data knows that least squares or linear regression works very bad. Here you see I'm trying to fit a line to the blue dots, and I've got two outliers, and you see how in the red, the linear regression solution is attracted to the outliers. But if I lose a robust regression, which is the loss function on the right here, which is quadratic when the error is small, but then turns into an absolute value, then you can ignore the outliers. And this is very common in signal processing from the 80s, all those robust statistics algorithms. Specifically in our problem, as I said, we have, this is my student, Yoav drew this very nicely. The inputs here are the umbrella and the river, the height of the river and the amount of rain yesterday. The output is going to be the height of the river today, and we want to do it on many, many points around the river. So we're trying to solve this huge linear regression problem, W times X. We want to find the W such that W times X will be as close as possible to Y. And the problem is W is huge. So we want to use knowledge about the problem structure and reduce parameters. I'm not going to go over this because I don't have time, but basically we're going to use something called Gaussian graphical models, which says that if I look at the river, I can construct a graph from it and know that there are many zeros in the matrix here. I'm jumping on it because we don't have time, but this is a full lecture. And indeed, the linear regression solution is Y as a function of x as these gamma matrices times x. And the gamma function matrices, we know that they will usually have zeros, okay? And we know that because of the geography. And that's something called Gaussian Markov random field, GMRF. People have been using it for years now. It's the Markov random field is exactly the sparsity. The Gaussian is the fact that the likelihood here is the quadratic Gaussian approach plus the log det. And it's a convex optimization. It works very, very fast, but it is not robust, as I said. Least squares, linear regression, Gaussian doesn't work well with outliers. On the other hand, there are the elliptical models. Elliptical models is you replace the quadratic function with this rho. People have been doing it for many years. This works great in practice, but once you combine it with graphical models, it is not known whether it is possible to solve such problems efficiently. Let me just show you some references. So here are many references on extending the Gaussian graphical models to generalized Gaussian. Think of Laplace, angular distribution, Tyler, t-distribution, Huber, trimmed, many papers, all of them trying to combine robust statistics with graphical models. Again, robust statistics replace the quadratic function by something that looks more like an absolute or a log, where graphical model assumes that there is structure. Our main work from NIPS 2019, NeurIPS 2019, shows that indeed all these works succeed because the problem is somehow easy, theoretically. What do I mean? We prove that once you have enough samples and the likelihood approaches its population, then any stationary point of this loss is globally optimal, although this problem is non-convex. So all the people that succeeded before, now we understand why they succeeded, because the problem has no bad stationary points. And I think, at least in my group, one of the things that we are most interested in is understanding which problems are like hard and which are easy. And by easy, these are problems where you can just start anywhere, do gradient descent, converge to a stationary point, and you know that any stationary point is globally optimal. So this is exactly the case here, although the function is non-convex. Okay, let's see some experiments. These are experiments in the stock market, less interesting. Let's see experiments in river discharge. So you see here lots of curves. Let me try to explain what they are in the 2 minutes I have. So let's start with the brownish ones. We see mean squared error is a function of training samples. So the brownish ones are 3 curves. All of them are unstructured, no graphical models. Okay, lots of parameters. That's why they need lots of samples to get good accuracy. You see they need at least 200 samples to succeed. The worst one is the Gaussian one, the GMRF. Below it is Laplace, and then Tyler. Tyler is even more robust than Laplace. And you see exactly the intuition that in them, all of them don't exploit sparsity, but they do exploit robustness. If you use a more robust loss function, you get better accuracy. Then let's go to the left. You see, again, we have the 3, the Gaussian, Laplace, and Tyler, yellow, red, and some blue color. But all of them are now structured. What do I mean by structured? We look at the geography, and whenever 2 sites are geographically distant, we put a 0 in their inverse covariance. And again, you see the advantage over the full estimators, and you see the advantages of Laplace and Tyler over the Gaussian one. Now we have another walk on doing this even more efficiently by using conditional Markov random fields, but I will skip through this. And just in time, 49 minutes. I have 20 more seconds, and we can meet the questions.
All right. Thank you, sir, for this hugely informative and interesting webinar. We will be moving on to some questions which I've collected from the mails and the live chat. So the first question is, what is the scope of this technology and topic in India and outside?
What is the scope? Okay, first, again, I want to start by a disclaimer. I work in the university. I mostly do the theoretical part. This is more a question for the leaders of the flood forecasting team in Google, which is now huge. When I started there were 5 people. I think now there are a few dozens people. So I probably don't know exactly. What I think the goal at the end of the day is to be able to do this in a huge scale. What do I mean? Right now, in the first year, we did it only in the Patna region. That was, I think, very exciting, but I think that's not what people have in mind when they started this project. The main idea is to make it completely automated and to be able to really do it in a global scale, so that you can just anywhere, for example, in India and outside India, I know they are now collaborating with other countries, that you can deploy the system with minimal calibration. Right now, every place we deploy it, we need to do a lot of calibration for the specific location. So we want everything to be automated and that it will work as is, with as little engineering as possible. This is the main goal. Another thing is that that this year we'll try for the first time is also to use machine learning for forecasting. As I said, up till now, in the last 2 years, in the monsoon region, all the forecasting was done by the Indian government. And of course, there are many other challenges that the group is, which I know even less about. Now they're talking about flash floods. They're also talking about other disasters, from earthquakes to climate change and many exciting things, which I am not, I don't know enough about to talk.
All right, that is a satisfactory answer. The next is, which language or software is currently in trends with respect to signal processing and the processing which we have done here?
Again, can you ask?
Yeah, which software or which language is currently in trend with respect to the signal processing?
I use Python. You mean which language? You mean which computer language?
Yeah.
I use Python, but I always tell my students, just use whatever you can to get it done.
Okay.
The students are always better than the professors as far as choosing the most the up-to-date software. And I don't think it really matters. I mean, you should use whatever. The algorithms are the same. I mean, it doesn't matter if you work in MATLAB, Python. Like, I think this, like, here in everything that was developed here, I think, for example, the differential equations were designed originally on Python, but then to scale because we needed to really run it in large scale, everything was translated to C. I personally don't remember how to program in C. It's been too long.
Okay. All right. The next is, all the data which we have used here, do we have a link to it? How can we get access to all these data, the satellite data and the hydraulic data which we had?
Great question. So everything we used in the papers is freely available and it has nothing to do with Google. Most of our training in the papers, what we did in the papers, the discharge was always from rivers in the United States. And then if you look at their website, the United States, it's called USGS, geologist something, and you can download everything from there. And then the satellite information you can download from Google Earth. They also have You can also download it from Landsat itself, but it's more convenient to download it from Google Earth. It doesn't belong to Google Earth. Google Earth just gives you a nice interface to it. Syncing them together takes a bit of time because you've got data sets of the discharge and the satellite, so you need to somehow sync them together. If somebody wants to reconstruct our specific experiments, I can send them the data that we used. Now, the data, some of the papers I think I mentioned on the hydrology in India, this is data from India. There, I think the data belongs to India. I didn't work on that. If you want access to it, send me an email and I will connect you with the person who wrote that paper and they can help you. But if you just want science, my best advice is just use Google Earth. It will not be data from India, but you can try out the algorithms, and then when it works, you need to somehow collaborate with the government to get data from India.
Okay. So we'll also keep, for the viewers of future, we'll also keep the email ID in the description. Right. So next question is about a specific question. It is, in NDWI, I am trying to understand how you go from 11 images to 1 image. Is there something we are missing?
You just, there was a formula there. It's actually, NDWI it doesn't really use all the 11. We use all the 11. NDWI, the simplest one, uses actually only 2 images. I don't remember what it is. Let me go back in my slides. I think it was the near infrared. Let me go. I don't think you see it, but I think it was near infrared and near shortwave. Yeah, shortwave infrared and near infrared. So you take the image of the near infrared, subtract the shortwave infrared, and divide it by their sum. So you started off by 2 images, and you get 1 image. There's also something called modified NDWI, and many others that use a few more bands, lots of complicated formulas. In our specific algorithm, what we did was a linear combination. You remember this W that we learned? This vector W? So W1 multiplies the first image, then you add W2 times the second image, plus W3, the third image, and you do it. W, the size of it is 11. And that's how we got to we go from 11 images to 1 image. Did this happen? Okay.
I hope it does. So the next question, maybe the last one, the question is how to open remote sensing high resolution images.
Again?
It's how to open remote sensing high resolution images.
What do you mean?
Maybe they're referring.
How to
maybe
open?
They are referring to some software or some. Maybe they're referring to the.
I mean, you can do it. I don't know. Every student of mine does it using a different software. I use Google Earth. I download it from Google Earth directly to. If you guys, I recommend using something called Colab. You know what Colab is? Colab is it's a Python environment IDE in Google that it's on the cloud, and it's directly. It's very easy to download from Google Earth, which is also Google, to Colab, and then you just work on it on Python. You can just say exactly which area you want at which time, and you get it on Python. If on the other hand you want, Google Earth on its own has a JavaScript script language on it, so then you can work directly on Google Earth.
Okay, so that was the last question. I think the Q&A is over. So again, IEEE SPS DC is grateful that you took out your precious time to share your knowledge with us. A big thank you to you. Right?
Thank you very much.
Before we
wrap up, to everyone.
Yeah. Thank you.
Bye-bye.
So before we wrap up, bye-bye. Before we wrap up, an interesting news for all our viewers. IEEE Signal Processing Society's international flagship conference ICAST 2020 to be held in Barcelona, city of Spain from tomorrow, that is May 4 to May 8, 2020, is going completely virtual and the best part is it's all free of cost. So it's a golden opportunity for all our members to be able to attend this event, and the registration link is available in the description too. Please go and have a look. Also, if you are interested to join IEEE SPS, this is again a golden chance. Currently, the Signal Processing Society membership costs only half the actual price, which is $1. The actual price is $1. If you are interested, you can just have a look. You may please contact us for any assistance. I request you to please stay tuned to our media handles for updates on more such events, and the references are most welcome. Thank you for all our viewers. Thank you.